Good morning guys. Today we will start our next unit, that is unit 6, dynamic analysis. Okay, so up to this we have covered our 5 units. That is, first one is your introduction, second one is your one dimensional, third one is your two dimensional problems, fourth one is your isoparametric elements, fifth one is your FEA-2 heat transfer problems, and now this is the last one, that is the finite elemental formulation for dynamic analysis, that is vibration analysis problems. Okay, so in our previous units we have determined, in generally for static problems we have determined the displacements, stresses, strains. Then in heat transfer problem we have determined the heat transfer, the temperature distribution within the element, that is heat generated, heat going inside, heat going outside the body. Okay, now in this unit we will determine the dynamic nature of the problem. Okay, that is we are going to determine the frequency. Okay, so these problems are related to your time domain. Okay, so in these previous problems, these are the time invariants, and these problems are the time variant, or we can say the we will determine the frequencies. Okay, or we can say the mode shapes of the problems. Okay, so this is your dynamic analysis. So actually in static problems we have this static analysis, it is a time invariant, but in dynamic analysis we will determine the frequency, that is the time dependent parameter. Okay, so for this case we need a governing differential equation to have the finite elemental formulation. So we need the governing differential equation for this dynamic analysis. As in previous case for heat transfer problem we had governing differential equation for one dimensional steady state heat conduction problem. So similarly we need governing differential equation to this dynamic analysis. Okay, so we need this governing differential equation for this free vibration case or forced vibration case. So here our syllabus is limited to free vibration analysis of the rod. Okay, so in this case we need this governing differential equation. Then by using this governing differential equation we can apply our finite elemental formulation to this governing differential equation to obtain the mass matrix as well as stiffness matrix. Okay, so in this way we will find out our mass matrix and stiffness matrix by using, in previous problems we used actually the Galerkin approach to get the elemental stiffness matrix. Okay, now in this case we are going to apply the weighted residual approach. Okay, now this weighted residual approach, it is given by this equation. Weighted residual, or you can say this is similar to the weighted residual function, or you can say the shape function into residual into dx is equal to 0. Now this residual, it is nothing but the governing differential equation for that dynamic analysis. Okay, now we will see how to apply this weighted residual equation to this dynamic analysis. So first we need the governing differential equation. So the governing differential equation, and these problems are time dependent. Okay, these are not steady problems or static problems, these are time dependent problems. Okay, so because the static problems are time invariant, okay, but these are the time dependent problems because here the displacement, it is a function of time, this u is the function of time as well as displacement. Okay, so the governing differential equation for free vibration, one second. So governing differential equation, the governing differential equation for undamped free vibration, for undamped undamped free vibration of a rod is given by dou by dou x in bracket EA dou u by dou x minus rho a dou square u by dou t square is equal to 0. Okay, so this is the governing differential equation for undamped free vibration of a rod. It is nothing but dou by dou x EA dou u by dou x minus rho a dou square u by dou t square is equal to 0. Here we are going to derive our elemental stiffness matrix or elemental mass matrix for this rod. Okay, so here u is nothing but the axial displacement. U is the axial displacement function. Then E is nothing but your Young's modulus. Okay, this is the Young's modulus of elasticity of the rod. A is the area of cross section of the rod, and this rho is the density of the rod. Okay, so E Young's modulus, A is the area, rho is the density of the rod, and U is the displacement function of the rod. Okay, so now from this governing differential equation, let us suppose, because this is equation 1, we will get our residual for this weighted residual method. Now this LHS side, it is nothing but, it is considered to be a residual. Okay, now by using weighted residual method, okay, so by using weighted residual method, actually we have studied this method in your first week, or you can say as a WR method. So instead of Galerkin method, we are using here weighted residual method. Okay, so in previous lectures or for previous units, we have applied Galerkin method or Galerkin approach to derive the elemental stiffness matrix. But in this case, we are going to use weighted residual method. In this case, this residual, it is nothing but the governing differential LHS of this governing differential equation. This weighted W is nothing but the weighted function, or you can, it is similar to the shape function. Okay, so if we apply or if we put this residual into weighted residual method, we will get here. So actually this is nothing but we are going to derive the elemental stiffness matrix or elemental mass matrix for this undamped free rod. Okay, so to have the natural frequencies of this rod. So here integration 0 to L. L is nothing but the length of rod. Okay, so from initial limit 0 to final limit L, this is given by integration 0 to L. Then this W into this residual into dx is equal to 0. So by putting this equation, by putting this residual into this equation R, we will get integration 0 to L, this W into this equation. So this equation is what? Dou by dou x of EA dou u by dou x minus rho a dou square u by dou t square dx is equal to 0. Okay, now this weighted W is nothing but the weighted function. Okay, or it is similar to the shape function. So this is given by W is nothing but W1 N1 plus W2 N2. Okay, and you can write this as W1, W is equal to W1 W2 into N1 and okay, so you can write this weighted a function as w1 n1 plus w2 n2, where n1 and n2, this n1 and n2 this is similar to the previous case, like n1 is equal to 1 minus x by l and n2 is equal to x by. Similarly, the u, this displacement function is given by u is equal to n1 u1 plus n2 u2. Okay, or you can write this in matrix format as, because we have already studied these concepts of this n1, what is this n1, n2, what is this u, how to write this u. Okay, so u is nothing but n1 u1 plus n2 u2, or you can write this n1 this as n1 n2 into u1 u. Okay, so in this way you can write this u as u1 n1 plus u2 n2, that is n1 n2 into this vector u1 u2. Similarly, this weighted function as w1 n1 plus w2 n2, or you can write w1 w2 into n1 n2, where n1 and n2 these are the shape functions, and its values for this rod element is given as 1 minus x by l and x by l, because we have considered a two-noded element, okay, of length n, where this is first and this is second. Okay, so same procedure we have applied. So that's why, in short, I am telling this that u can be written as n1 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 u1 plus n2 u2, and this can be written as w1 n1 plus w2 n2. And in terms of matrix, you can write like this. Okay, you can write like this. Okay. So now we will solve this equation of this weighted residual, and we will get our final elemental matrices. Okay. So this is the equation. So here, by multiplying, okay, here we will multiply this w2 whole equation. So we will get integration 0 to l. So w into dou by dou x ea dou u by dou x minus integration 0 to l w rho a dou square u by dou t square d minus is equal to 0. Okay. So in this case, in this way, we have simplified this like that. So w into this first term, w into this second term. Okay. Now, so by solving, so now we need to solve this equation. Okay, so how to solve this equation? So by using the by-parts rule. Okay, so by using by-part rules, we need to solve this equation. So by using by-part rule, so to this equation only, okay, 1 second. Okay, so we will apply our by-part rule to solve this equation. So first, actually this is the function of x, so we need to solve this by using the by-part rule, and it is the function of a time. So we don't need to solve this by using the by-part rule, because w it is only the function of x, but this is the function of t. So only with respect to x, here it is a simple integral. But in this case, this w is also a function of x, because w1 n1 plus w2 n2, and n, as we know that w is written as w1 n1 plus w2 n2, and n1 and n, this is the function of x itself, because n1 is nothing but 1 minus x by n, and n2 is nothing but x by n. So that's why this w is function of x. Here it is a function of x. Also, this total term is also a function of x. So this is first, if we consider this term as u and this term as v, then by applying the by-part rule, as we know that the by-part rule is written as integration of uv dx is equal to u integration of v dx minus integration of du by dx integration of v dx. Okay, so by using this by what rule to this equation we will write w u v. It means w integration of dou by dou x EA dou u by dou x dx over limit 0 to minus integration du by dx, that is dw by dx, w by dx into integration of this second term dou by dou x in bracket EA dou u by dou x dx minus this remaining term integration 0 to L w into rho a dou square u by dou t square dx is equal to 0. Okay, so in this way we have written by now we need to solve this. So this will become, so integration of this term will become only this term, because integration of derivative of this term means integration of, so it will become only here, it will remain only this term. So w into EA dou u by dou x over limit 0 to n minus integration dou w by dou x into integration of this term is only remaining this term. Okay, so this will become EA dou u by dou x into dx minus integration 0 to L w into rho a into dou square u by dou t square dx is equal to 0. So in this way we have simplified this first term. Okay, now we need to write down in terms of w1 and w2. So in terms of w1 and w2 we will write down. So as we know that this can be written as this term at L minus this term at 0. So in that case this term at L means at second node w2 will be responsible function. Okay, so this will become, so from here I will write w2 into EA dou u by dou x minus, for 0 it will become w1, because we know that this is the rod. For second case w2 will be applied, for first case w1 will be applied. So for second case w2 EA dou u by dou x minus w1 into EA dou u by dou x. Okay, so minus integration. So as we know that w is written as w1 w2 into n1 n2. So if we take the derivative of this case, it will become w1 w2 into dn1 by dx dn2 by dx. Okay, so here we will write down integration 0 to L. So instead of dw by dx we will write down w1 into w2. So w1 W2 into this vector. This vector is nothing but dn1 by dx, dn2 by dx, because this w is function of n1 and n2. So n1 and n2 is function of x. So we need to take derivative with respect to n1 and n2. So this will become dn1 by dx and dn2 by dx. Okay, into EA into dou u by dou x. Now we know that u is written as n1 and 2 times u1. Okay, so by using this u, we can write down this as n1 and 2 with respect to u. So this will become, because u is the function of n1 and n2, so it will become dn1 by dx. So this will become as dn1 by dx, dn2 by dx into u1 u2. Okay, dx. So instead of u, so dou by dou x of u, but u is the function of n1 and n2, and n1 and n2, these are the functions of x. So we can write, instead of n1 and n2, means taking derivative with respect to n1 and n2, we can write EA into dn1 by dx, dn2 by dx into this u1 u2 into dx. Okay, so this term can be replaced by this minus last term is what? So for last term, we need to write down, instead of w, we need to, okay, here, instead of w, we need to write down w1, w2, and 1, and 2. Then rho a into dou square u by dou t square. Now, in this case, dou square u by dou t square, it means dou square, here, it is a function of t. So we need to write down dou square u1 by dou t square, dou square u2 by dou t square. So here we will write down this term as minus integration 0 to L w, instead of w, we will write down w1 w2 into n1 n2 into this rho a. Now this can be written as this is the function of t. So we can write down with respect to t, we can write down dou square u1 by dou t square, and for second node dou square u2 by dou t square. So as we know that if u is the displacement function, then u dot, it is the first derivative, and u double dot, it is the second derivative. So for this case, we can write, for simplicity, this is as u1 double dot and this is as u2 double dot. So instead of this dou square u1 dou t square, we can write rho a into u1 double dot and u2 double dot into dx is equal to 0. So in this way we have written, or we have simplified this equation. Okay, now we will just solve this integration to get the elemental stiffness matrix. Okay, so here, now these two equations, it can be written as, in terms of matrix form, it can be written as w1 w2 into minus EA dou u by dou x, EA dou u by dou x. Okay, so we can write these two terms in matrix form as w1 w2 minus, because if we multiply this w1 into minus EA dou u by dou x, w1 into minus EA dou u by dou x, this is this term, w2 into this two. So here is the term. So we can write these two terms in terms of matrix as like this. Okay, so this can be replaced by this term minus total this term minus this term minus this term is equal to 0. So here now we can eliminate this matrix W1, W2. Here it is common. Here it is also, this matrix is also there. Here in this third term, this W1, W2 matrix is there. So by eliminating this, we will get final equation as minus EA dou U by dou X, EA dou U by dou X. Now these two minus terms, here I am transferring it to RHS side. So this will become equal to, this will become integration 0 to L. This will get cancelled, this will get cancelled. So this will become dou N1 by dou X, dou N2 by dou X into EA into this matrix dN1 by dx, dN2 by dx into U1, U2 dx plus, because we are transferring this term from for other side, so it will become plus integration 0 to L, 0 to L N1 and 2 into N1 and 2, N1 and 2 into rho times A into N1 and 2. Sorry, here N1 and 2 should be there actually. Here N1 and 2 should be there, because as we know that U is equal to N1 and 2 into U1 U2, and we have taken second time derivative with respect to t, so this will become constant. So this constant should be there. Actually, we have this term here. So N1 and 2 into this U1 double dot U2 double dot. Okay. N1 and 2 into this U1 double dot U2 double dot into dx. Okay, so we have written these terms like that by eliminating this W1 W2 matrix. Okay, so now we need to simplify this matrix. Okay, so these two terms on LHS side and this third term on RHS side. Here we will write down these two terms on LHS and this third term in RHS side. So here, so this will become integration 0 to L, that is integration 0 to L, EA, we will take it as common, EA into integration dou N1 by dou X into dou N2 by dou X into this matrix dou N1 by dou X, dou N2 by dou X into U1 U2 dx plus integration 0 to L here EA, here rho A should be there. That is will be also rho A, rho into A dot into N1 and 2 into N1 and 2 times U1 double dot U2 double dot into dx is equal to this first one. Is equal to minus EA times dou U by dou X and plus EA times dou U by dou X. Okay, now we need to simplify these matrices term, that is we need to take multiplication of these matrices so to solve the equations. So if we multiply this matrix into this matrix, we will get integration 0 to L EA. Now multiplying this matrix into this matrix, we will get 2 by 2 matrix. So this row into this column, we will get a 2 by 2 matrix. Like this row into this column, we will get dou N1 by dou X into dou N1 by dou X. We are just multiplying. this row into second column will get dou n1 by dou x into dou n2 by dou x, because here we will get 2 by 2 matrix by this multiplication. Now this second row into first column, this will become equal to dou n2 by dou x into dou n1 by dou x. Now second row into the second column, that is dou n2 by dou x into dou n2 by dou x. Okay, so this will become like integration 0 to L EA times this into u1 and u2 times dx, plus similarly we need to multiply these two matrices, this into this. Similarly here we will also get 2 by 2 matrix, this row into first row into first column. So here this will become integration 0 to L row times A into first row into first column, that is n1 square, first row into second column, that is n1 and now second row into first column, that is n1 and second row into second column we will get n2 into u1 double dot u2 double dot into dx is equal to this term. So finally we will get this integration. Okay, this is actually equal to, we will write down, minus EA dou u by dou x plus EA dou u by dou x. Okay, now we need to solve this integration. So for this case we need n1 n2. So n1 is nothing but 1 minus x by L, n2 is nothing but x by L. So this dou n1 by dou x, it will become minus x by L, and dou n2 by dou x, this will become 1 by L. With respect to x, this will become 1 by L, because with respect to x we will take derivative with respect to this. So minus 1 by L, and dou n2 by dou x will become 1 by L. So by putting, so we know that dou n1 by dou x is equal to minus 1 by L, and dou n2 by dou x is equal to 1 by L. So we need to put these values into this equation. So we will get integration 0 to L EA in bracket. So this is dn1 by dx, that is minus 1 by L into minus 1 by L. Then this minus 1 by L into 1 by L. And for this case 1 by L into minus 1 by L. For this case 1 by L into 1 by into u1 u2 dx. Okay, plus integration 0 to L rho A. So instead of this we can write 1 minus x by L bracket square, 1 here 1 minus x by L into x by L, then 1 minus x by L into x by L, for this case x by L bracket square into u1 dot u2 dot dx is equal to this term. Okay, now we need to just solve this. So this will become this will become, this matrix, it is a constant matrix, so we can write it as minus 1 by n, 1 by L square. This is minus 1 by L square. This term is minus 1 by L square, and this term is 1 by L square. Okay, into integration 0 to L, this is this row EA should be there. This EA into this matrix, because this is constant matrix. EA is also constant term. So integration 0 to A. Remaining is what? Here U1 and U2 is also remain. U1 and U2 is also constant term. Into integration 0 to L dx plus integration 0 to L. Now this row A is constant into 1 minus x by L bracket squares. It is, we need to expand this. So 1 minus 2 times x by L plus x square by L square. Similarly, we need to multiply this. So x by L minus x square by L square. Here we are writing this in matrix form. So this is first term. This is second term. Similarly, we will get third term. X by L, that is x by L minus x square by L square. This is third term. And x square by L square into u1 double dot u2 double dot dx is equal to 0. This is this term will be carried. Okay. So finally we will get. So here we will get EA into, now integration of this is L, because integration of dx is x over limit 0 to L. So this will become L minus 0. So finally L. Okay. So L square and L square. This L, it is common to all this matrix. So we can write EA into L. So here we can write EA into L, E into A into L. So if we multiply that, E into A into L into this matrix. So this L will get cancelled. Each L will get cancelled. So this 1 by L will be a common. So we can write this as EA by L. So 1 by L it is A. We have taken this as a common. So this matrix will remain as 1 minus 1 minus 1 1 into U1 U2 plus. Okay, so this integration we need to take for each term, that is integration over 0 to L, integration over 0 to L, similarly integration over 0 to L, similarly integration over 0 to L, and to solve, and we will solve this integration. So plus this will become rho times A into, now integration of this will become x minus 2x square by 2 times L plus x cube by 3 times L square over limit 0 to L. Then second term, x square by 2 times L minus x cube by 3 times L square over limit 0 to L. Then for third, x square by 2 times L minus x cube by 3 times L square over limit 0 to L. And finally x cube by 3 times L square over limit 0 to L into this U1 double dot and U2 double dot is equal to this term angle. Okay, so here we have simplified this term. Now we will concentrate to simplify this term. Okay, so this will become plus, so this is the same term, into rho A in bracket. So if we, here we have taken integration, so now we need to put, instead of x we need to put these limits. So L minus 2 times L square by 2 times L plus L cube divided by 3 times L square. Then L square by 2 times L minus L cube by 3 times L square. Okay. Then L square by 2 times L minus L cube by 3 times L square. And finally L cube by 3 times L square. This is the matrix. So this will become finally this will become plus rho A in bracket. Now L minus, this will become L minus this L square 2 will get cancelled, L minus this will get cancelled, L by 3, sorry, plus L by 3. Then this will get cancelled, so it will become L by 2 minus L by 3. So here L by 2 minus L by 3 and L by 3. So finally this will become, so this matrix will become L minus L, it will get 0, so here only L by 3 will be. So L by 3, here 3 minus 2L, L by 6, so this will become L by 6, this will become also L by 6, this will become L by 3, L by 3 into U1 double dot and U2 double dot is equal to this remaining term, that is minus rho A, sorry, EA dou U by dou X and EA dou U by dou X. Okay. So here if we take L by 6 as a common, so this will become 2 times L by 6, this will become 2 times L by 6, because if we simplify this, it will become L by 3, this also become L by 3. So we need to take now L by 6 as a common, so this will become as rho into A into L divided by 6, it will get as a common, so this will become 2, 1, 1. So in this way, finally we will get this matrix as rho into A 2, 1, 1, 2 into this U1 double dot into double dot EA into A by L into this matrix into U1 into plus this matrix into U1 double dot into double dot is equal to this matrix. So finally, okay, so this is the final derivation, final equation of this free vibration of this rod. Okay, so if we write down this as rho A into L divided by 6, so rho A into L divided by 6 in bracket 2, 1, 1, 2 into U1 double dot U2 double dot plus EA by L into 1 minus 1 into U1 U2 is equal to this minus EA dou U by dou X and EA dou U by dou X. So this will become, so this is your mass matrix, elemental mass matrix. This is your elemental stiffness matrix. Okay, and this is your load. Okay, so by this we can write it down now. M into U double dot plus is K into U is equal to this force or load left down. Okay, so in this way we will get this equation. Like for free vibration, as we know that for free vibration analysis, we know that the equation, that is M. So as you studied in your free vibration subject, that the free vibration equation is given by mx double dot plus Cx dot plus Kx is equal to 0, where Cx dot, this is related to your damped vibration, but we are actually studying here undamped free vibrations, so this will become equal to 0. So finally this for free undamped free vibration, this equation will become mx double dot plus Kx is equal to 0. So this is your mass matrix, this is your stiffness matrix, and this is your load vector. So in this way we have derived the elemental mass matrix, also elemental stiffness matrix for this rod. Okay, so this is your mass matrix, and this is your stiffness matrix, and this is your load vector. Now by using this equation, now we will see two such different cases, that is consistent mass matrix and lumped mass matrix. So by using this consistent mass matrix, what will be the effect? By using this lumped mass matrix, what will be the effect on this mass and stiffness matrix? Okay, so by using these two approaches, now in next lecture we will solve our examples related to your vibration analysis of this rod. Okay, so here I am concluding this lecture. So thank you. In next lecture we will solve some examples. Okay, thank you.